Have you ever had that feeling? That strange, prickling sensation on the back of your neck that you're not alone, even when a room is completely empty. Or that feeling when you're walking through an old forest, a sense of an unseen presence, a weight in the air that you can't quite explain? We often dismiss these feelings as tricks of the mind, our ancient survival instincts playing games with us. But what if I told you that on a cosmic scale, that feeling is absolutely, demonstrably real? What if the universe you see, the stars, the galaxies, the planets, everything you've ever learned about, is just the foam on the crest of a deep, dark, invisible ocean? Welcome to the story of dark matter. It's a story that suggests 85% of all the matter in the cosmos is completely invisible to us, a hidden reality whose gravitational influence is the only reason our galaxy holds together, the only reason we are even here to ask the question. In this video, we're going on a journey to the edge of what we know. We'll look at the iron-clad evidence that this invisible reality must exist. And then we're going to look at the unsettling possibility that we might be completely wrong, and that the greatest mystery in science might not be a missing thing, but a fundamental flaw in our understanding of reality itself. So grab a drink, get comfortable. We're about to peel back the curtain on the visible world. An invisible universe. Let's start with a simple but mind-shattering fact. Everything you see, everything you can touch, every star in the sky, every grain of sand on every beach, every atom in your body, all of it makes up less than 5% of the known universe. Let that sink in for a moment. If the universe were a vast library containing all the knowledge of existence, we have only ever been able to read 5% of the books. The rest of the library, the overwhelming majority, is written in an ink we can't see, on pages we can't touch. This isn't science fiction or some new age philosophy. This is the consensus of modern cosmology, an uncomfortable truth we've been forced to accept over decades of observation. We call this missing stuff dark matter and dark energy. The name dark isn't meant to sound spooky, though it kinda does. It simply means it doesn't interact with light. It doesn't shine, it doesn't reflect, it doesn't absorb. It's utterly, totally transparent. It's the ultimate ghost passing through you, me, and the entire planet right now, as if we weren't even here. But this ghost has weight, a lot of it, and its gravitational pull is the silent conductor of the cosmic orchestra, shaping the universe we know, while remaining completely hidden from view. This raises the most profound questions imaginable. Is this dark matter just a single, boring, lonely particle floating through the void? Or could it be something more? A dark sector, with its own family of particles, its own forces, maybe even its own complex dark chemistry? Are we living alongside a parallel, invisible reality that has shaped our own existence from the very beginning? This is the grand mystery we're here to unravel. The first clues. Our story doesn't begin in a modern billion-dollar laboratory, but in the 1930s with a brilliant and famously difficult Swiss astronomer named Fritz Zwicky. Zwicky was a character. He called his colleagues spherical bastards because, he said, they were bastards no matter which way you looked at them. But he was also a genius. While studying the Coma cluster, a massive swarm of over 1,000 galaxies, he noticed something deeply wrong. He measured the speed of the galaxies orbiting the cluster center, and they were moving astonishingly fast. He did the math, using Newton's laws of gravity, to figure out how much mass the cluster would need to keep those speedy galaxies from flying off into deep space. Think of it like spinning a weight on a string. The faster you spin it, the stronger your hand has to be to hold on. Zwicky calculated the gravity needed, and then he counted up all the visible matter from the light of the galaxies. The numbers didn't match. Not by a little, but by a staggering amount. He calculated that there had to be over 400 times more mass than he could see. He called this missing mass dunkle materie, or dark matter. For decades, the scientific community largely ignored him. His colleagues thought he was an eccentric crank, his measurements probably flawed. The idea lay dormant into the 1970s, when a determined astronomer named Vera Rubin, a woman who had to fight for her place in a male-dominated field, gave the idea its second, undeniable life. She wasn't looking at galaxy clusters, but at individual spiral galaxies, like our own Milky Way. The expectation was simple. Just like in our solar system, where the outer planets, like Neptune, orbit much more slowly than the inner planets like Mercury, the stars on the outer edge of a galaxy should be moving much more slowly than the stars near the bright, dense center. Rubin and her colleague Kent Ford developed incredibly sensitive equipment to measure the speed of these stars. And what they found was shocking. The stars on the outer edges of the galaxies were moving just as fast as the stars in the middle. This is just wrong. It breaks the laws of gravity as we know them. The only way this could be possible is if the galaxy was embedded in a massive, invisible halo of something. Something that didn't shine, but had immense gravitational pull. Vera Rubin had found Zwicky's ghost not in a distant cluster, but in our own galactic backyard, holding galaxies together. Let's really break down what Vera Rubin found, because this is the single most powerful piece of evidence for dark matter. It's called the galaxy rotation curve. Picture our solar system. Mercury, close to the Sun, zips around in just 88 days. Neptune, way out on the edge, takes 165 years. This is because the vast majority of the mass in our solar system is concentrated in the center. In the Sun, gravity gets weaker with distance, so things farther out move slower. It's intuitive. We expected galaxies to work the same way. All the bright, shiny stuff, the stars, the gas, the dust, is concentrated in the galactic center and the spiral arms. As you move to the outer edge of a galaxy's disk, where it gets faint and empty, the stars should slow down dramatically. But when Rubin measured their speeds, they didn't slow down. They stayed at a high, constant speed, way out into the galactic suburbs. This flat rotation curve is a cosmic smoking gun. It's like watching a merry-go-round where the horses on the outer rim are spinning just as fast as the horses near the center. To make that happen, the merry-go-round can't be a flimsy platform. It has to be a solid, heavy disk. For a galaxy, the implication is staggering. The visible disk of stars must be embedded in a vast spherical halo of invisible matter that extends far beyond the visible stars. The gravity from this dark matter halo is what's gripping those outer stars and whipping them around at such high speeds. This isn't a small error. The math shows that to account for these rotation speeds, this dark matter halo has to contain somewhere between 5 and 10 times more mass than all the visible matter in the galaxy combined. It is, for all intents and purposes, the true substance of the galaxy. The stars are just the pretty lights sprinkled on top. This is a fact that has been confirmed in thousands of galaxies. It's not an anomaly, it's the rule. Without this invisible cosmic glue, galaxies, as we know them, would tear themselves apart. Gravity's lens, bending the fabric of spacetime. If the rotation of galaxies was the first punch, gravitational lensing was the knockout blow. This proof comes straight from Albert Einstein and his theory of general relativity. Einstein taught us that massive objects don't just pull on other objects with a mysterious force. They actually bend and warp the very fabric of spacetime around them. And because light has to travel through this spacetime, its path gets bent when it passes by a massive object. Think of spacetime as a stretched rubber sheet. A bowling ball galaxy placed on it creates a deep well. A marble, a beam of light. Rolling past that well will have its path deflected. We can see this effect when we look at a very distant galaxy, and there happens to be a massive galaxy cluster sitting in the space between us and it. The cluster's immense gravity acts like a lens, a cosmic magnifying glass. It bends the light from the background galaxy, distorting its image into beautiful arcs, smears, and even multiple copies of the same galaxy, a phenomenon called an Einstein cross or an Einstein ring. Here's the crucial part. By measuring the amount of distortion, the way the light is bent, we can calculate precisely how much mass is in the intervening cluster. It's a way of weighing the cluster just by looking at how it bends light. And in every single case, the mass calculated from the gravitational lensing effect is vastly greater, again 5 to 10 times greater, than the mass we can account for by adding up all the stars and gas we can see. This is monumental. It's completely independent of galaxy rotation curves. It uses different physics, general relativity versus Newtonian gravity, and different observations, yet it arrives at the exact same conclusion. There is a colossal amount of invisible mass out there, dominating the cosmos. This isn't a theory anymore. This is a direct observation of dark matter's effect. We can't see the dark matter itself, but we can see the deep warp its gravity carves into the fabric of reality. The cosmic inventory. So we have multiple independent lines of evidence, all pointing to the same thing. But just how much of this stuff is there? By combining data from galaxy rotation, gravitational lensing, and another crucial piece of evidence, the cosmic microwave background (CMB) radiation, which is the faint afterglow of the Big Bang, cosmologists have been able to create a remarkably precise cosmic inventory, a recipe for the universe. And it's a recipe that should deeply humble us. First, let's talk about the matter we know and love. All the atoms, protons, neutrons, and electrons that make up you, me, the Earth, the Sun, and all the stars are called baryonic matter. This familiar stuff, the entirety of the periodic table, makes up just under 5% of the total mass and energy content of the universe. Next on the list is our mysterious culprit, dark matter. The calculations show that it makes up about 27% of the universe. This means, for every 1 kilogram of normal matter, there are more than 5 kilograms of dark matter. It is the dominant form of matter in the cosmos. It's what holds everything together. But that only adds up to 32%. What's the rest? Well, the biggest slice of the cosmic pie, a whopping 68%, is something even more bizarre and less understood: dark energy. If dark matter is the cosmic glue that pulls things together, dark energy is the opposite. It's a mysterious pressure that is causing the very expansion of the universe to accelerate, pushing galaxies away from each other faster and faster. It's a whole other can of worms for another time, but it's important to see the full picture. The visible universe is a tiny 5% sliver. The dominant gravitational force holding structures together comes from a ghostly 27%. And the ultimate fate of the universe, whether it expands forever or collapses, is controlled by an even more mysterious 68%. We are, in a very real sense, living in a universe that is almost entirely alien to us. The architect of the cosmos. Dark matter isn't just some passive, heavy freeloader in the universe. It's not just holding existing galaxies together. The evidence now shows that without dark matter, we wouldn't be here at all. Galaxies, stars, planets, none of it would exist. Dark matter, it turns out, is the universe's master architect. Let's go back to the very early universe, just after the Big Bang. The universe was an incredibly hot, dense soup of particles and radiation. It was also incredibly smooth, but not perfectly smooth. There were tiny, random fluctuations in density, some spots just infinitesimally denser than others. The problem is the intense radiation pressure in this early plasma was constantly trying to smooth these clumps out, pushing matter apart. Normal, baryonic matter on its own wouldn't have had enough gravitational juice to overcome this pressure and start clumping together. The tiny seeds of structure would have been erased. But dark matter was the game changer. Since it doesn't interact with light or radiation, it was immune to this smoothing pressure. While the normal matter was being tossed around, the dark matter particles, being much heavier and more numerous, could start to clump together purely under their own gravity. They began to form deep gravity wells. As the universe expanded and cooled, the normal matter was then able to fall into these pre-existing wells of gravity carved out by the dark matter. Dark matter provided the gravitational scaffolding. It was the skeleton, And the visible matter we see is the flesh that grew upon it. Our supercomputer simulations of the universe's evolution are incredibly powerful. When we run them with just normal matter, the universe remains a boring, diffuse gas. We never get galaxies or clusters. But when we add the 27% dark matter into the simulation, what we see is a miracle. Over billions of years, that scaffolding pulls matter together into a vast, beautiful network of filaments and nodes known as the cosmic web. And right at the densest intersections of this dark matter web, galaxies ignite. Our simulations with dark matter perfectly reproduce the universe we see today. Without it, the universe is a blank canvas. With it, we get the masterpiece, ruling out the obvious. Okay, so there's a ton of missing mass. But does it have to be some exotic new particle? This is the first question any good skeptic should ask. Couldn't it just be normal stuff that's hard to see? Maybe vast clouds of cold gas or dust. Or maybe the universe is filled with dim objects like dead stars, white dwarfs, neutron stars, failed stars, brown dwarfs, or rogue planets ejected from their solar systems. Scientists lumped all these possibilities under one banner, MACHOs, which stands for Massive Compact Halo Objects. It was a perfectly reasonable idea. And for a while, it was a leading contender against the more exotic particle theories. So, how do you look for something that's massive but doesn't shine? You watch it pass in front of something that does. In the 1990s, several projects, including one cheekily named the MACHO Project, did exactly this. They monitored millions of stars in a nearby satellite galaxy, the Large Magellanic Cloud, for years on end. The idea was that if a MACHO, a dead star, or a rogue planet from our galaxy's halo were to pass directly in front of one of those background stars, its gravity would act like a tiny lens. For a brief period, from a few days to a few weeks, it would magnify the light of the background star, causing it to brighten, and then fade in a very specific, predictable way. This is called gravitational microlensing. These experiments were a success. They did find microlensing events. They proved that MACHOs exist. But here's the crucial result. They didn't find nearly enough of them. The number of events they detected could only account for, at the very most, a few % of the mass needed for the dark matter halo. They simply ruled out MACHOs as the primary component of dark matter. We also know it's not clouds of gas or dust. Gas, even if it's cold, would still absorb or emit radiation at specific frequencies, like radio or X-ray. And we don't see that. Dust would absorb and redden the light of distant stars in a way that is also not observed. We've looked for the obvious culprits. We've checked under the cosmic rug for all the normal stuff we just might have missed. And it's not there. The answer has to be something new, something strange. The leading suspects. So, if it's not normal matter, what is it? We've now entered the realm of theoretical particle physics, a zoo of exotic possibilities. While there are many ideas, two main candidates have dominated the search for decades: WIMPs and axions. First up is a long-time frontrunner, the WIMP, which stands for Weakly Interacting Massive Particle. Let's break that down. Massive is key. They need to be heavy enough, perhaps 10 to 1,000 times the mass of a proton, so their collective gravity can do the job of holding galaxies together. Weakly interacting refers to how they experience the fundamental forces. They feel gravity, obviously. They are also thought to interact via the weak nuclear force, the same force responsible for certain types of radioactive decay. This is why they are so ghostly. The weak force is incredibly feeble and short-ranged, meaning a WIMP can pass through trillions of miles of lead without ever hitting anything. For a while, WIMPs were the favorite because of something called the WIMP miracle. Calculations showed that if a new particle with these properties existed, the Big Bang would have naturally produced it in almost exactly the right abundance to be the dark matter we observe today. It seemed too perfect to be a coincidence. But as the search for WIMPs has come up empty, another candidate has been gaining popularity: the axion. The axion is a very different beast. It's incredibly lightweight, potentially billions of times less massive than an electron. So how could it make up 27% of the universe? The answer is that there would have to be an unbelievable number of them, an ethereal sea of axions permeating all of space. The axion wasn't invented to solve dark matter. It was first theorized in the 1970s to solve a completely different problem in particle physics called the strong CP problem, which has to do with the symmetries of the strong nuclear force that binds quarks together inside protons and neutrons. The fact that this particle, invented for other reasons, also happens to be a perfect dark matter candidate is very compelling to physicists. A key property of the axion is that, under the influence of a very strong magnetic field, it could theoretically transform into a particle of light, a photon. And that gives us a clever way to hunt for it. The search deep underground. How on earth do you catch a particle that's designed to be almost undetectable? You go to the quietest place on Earth, and you build the most sensitive detector imaginable. Billions of cosmic rays, high-energy particles from space, are bombarding the surface of the Earth every second. Any signal from a rare WIMP interaction would be totally drowned out by this cosmic noise. So, physicists have gone deep underground, to the bottom of old mines or through tunnels bored into mountains, using kilometers of solid rock as a shield. Down in these ultra-clean, ultra-quiet labs, they build detectors like the LUX Zeppelin LZ experiment in South Dakota or the Xiononenti experiment in Italy. The core of these experiments is often a huge vat filled with a very pure, very dense liquid, usually xenon or argon, cooled to cryogenic temperatures. This tank is surrounded by thousands of incredibly sensitive light detectors. The idea is simple, even if the execution is breathtakingly complex. Trillions of dark matter particles, if they are WIMPs, should be streaming through the detector every second. Very, very rarely, maybe just a few times a year, one single WIMP will happen to collide directly with the nucleus of a xenon atom. This collision would be like one ghost momentarily bumping into another. The impact would cause the xenon nucleus to recoil, producing a tiny flash of light and knocking a few electrons loose, which are then guided by an electric field to produce a second flash of light. By detecting these two tiny, correlated flashes, scientists could say they have seen a dark matter particle. It's the ultimate needle in a haystack search, listening for the faintest whisper in a silent cavern, waiting for that one single ping that could change physics forever. So far, there has been silence. Creating dark matter on Earth. If we can't wait for dark matter to come to us, maybe we can make it ourselves. This is the goal at the world's most powerful particle accelerator, the Large Hadron Collider, LHC, at CERN in Switzerland. The LHC is a 27-kilometer ring of superconducting magnets that accelerate protons to 99.9999991% the speed of light before smashing them together with unbelievable force. In these collisions, according to Einstein's famous equation, E equals mc squared, the immense energy of the collision is converted into mass, creating a shower of exotic, short-lived particles. Physicists at experiments like ATLAS and CMS can't see dark matter particles directly in their detectors, for the same reason the underground experiments have trouble. They're invisible and weakly interacting. So they have to look for it by inference, by searching for missing energy. Imagine you smash two billiard balls together with a known amount of speed and energy. You can measure the speed and direction of all the pieces that fly off. If you add up the energy and momentum of all those pieces, it should equal what you started with, thanks to the laws of conservation of energy and momentum. But what if it doesn't? What if you smash your protons together, and you see a jet of familiar particles flying off in one direction, but nothing flying off in the opposite direction to balance the momentum? The only explanation is that something invisible and massive was created and flew off in that opposite direction, carrying energy and momentum away from the collision without leaving a trace in the detector. It's like a cosmic accounting error. By looking for events with this signature missing transverse energy, scientists at the LHC are hunting for the creation of dark matter particles. It's an incredibly challenging search, sifting through billions of collisions. But if they find a consistent signal, it would be revolutionary. Proof that we can produce the stuff that holds our universe together right here on Earth. Echoes of annihilation. There's a third way to hunt for dark matter, one that combines astronomy and particle physics. This is called indirect detection. The idea relies on a popular theoretical possibility that dark matter particles are their own antiparticles. In physics, when a particle meets its antiparticle, they annihilate each other in a burst of energy, producing a shower of more familiar particles, like high-energy gamma rays and neutrinos. If this is true, then in places where dark matter is thought to be extremely dense, like the center of our Milky Way galaxy, or in the cores of smaller satellite dwarf galaxies that are almost entirely made of dark matter, these annihilation events should be happening all the time. This process would produce a faint, diffuse glow of gamma rays. It would be a signature, a fingerprint of dark matter's self-destruction. So, astronomers use powerful instruments like the Fermi Gamma Ray Space Telescope and ground-based arrays, like the HAWC Observatory, to stare at these dark matter-rich regions of the sky. They are looking for an excess of gamma rays at specific energy levels, above and beyond what can be explained by normal astrophysical sources like pulsars or black holes. For a while, there was tremendous excitement. Scientists using the Fermi telescope did find a mysterious excess of gamma rays coming from the galactic center, with properties that looked tantalizingly like what you'd expect from annihilating WIMPs. However, as our understanding of the galactic center has improved, many astrophysicists now believe this excess can be explained by a large population of previously unknown millisecond pulsars, a more conventional, if still exciting, explanation. The hunt continues, but the ghostly signal of dark matter annihilation remains elusive, a whisper that we can't quite distinguish from the background noise of the cosmos. Is it really matter, or is gravity wrong? We have spent all this time discussing the hunt for a new particle. We've built massive experiments deep underground, smashed protons at incredible speeds, and scanned the skies for faint glows. All of this is based on one core assumption, that our understanding of gravity, from Newton to Einstein, is correct on all scales. But what if it isn't? What if there is no dark matter? What if the missing mass is just a phantom, a ghost we invented, because we are using the wrong law of gravity? This is the radical, and for some, deeply appealing, alternative idea known as MOND, or modified Newtonian dynamics. First proposed in the 1980s by Israeli physicist Mordechai Milgram, MOND suggests that Newton's famous second law, F equals ma, is not the whole story. Milgram proposed that when gravitational acceleration becomes incredibly weak, far, far weaker than anything we experience on Earth, on the scale of the outer edges of a galaxy, gravity behaves differently. It becomes slightly stronger than Newton's laws would predict. With this single, small modification to the law of gravity, you can explain the flat rotation curves of galaxies perfectly without needing a single particle of dark matter. It's not missing mass, it's extra gravity. For a long time, MOND was seen as a fringe theory, but it has had some surprising successes. It not only explains the rotation curves, but it also correctly predicts a tight relationship seen in galaxies between their total visible mass and their rotation speed, something the dark matter model has to work harder to explain. This is the biggest piece of evidence that dark matter might not be real. A competing theory can explain some of the key observations with elegant simplicity. However, MOND has its own serious problems. While it works well for individual galaxies, it fails spectacularly on the scale of galaxy clusters, where it can't account for all the missing mass. More importantly, it can't explain the gravitational lensing evidence from things like the bullet cluster, where we literally see the dark matter, via lensing separated from the normal matter. And most damningly, Mond offers no explanation for the cosmic microwave background data or how the large-scale structure of the cosmic web formed. To fix these problems, Mond advocates have had to invent their own more complex versions of the theory, sometimes even adding their own new particles, losing the initial simplicity that made the idea so attractive. The debate rages on: is it a new substance or a new law of nature? The dark sector, a hidden reality? Let's step back from the established evidence and allow ourselves to speculate for a moment. What if the truth is far weirder and more wonderful than we've imagined? The simplest models assume dark matter is just one type of stable, boring particle that doesn't do much besides have gravity. But why should it be so simple? Our visible world, the 5% of the universe we can see, isn't simple. It's a glorious mess of different particles, electrons, protons, neutrons, photons, neutrinos, and governed by different forces: electromagnetism, the strong and weak nuclear forces. This complexity allows for chemistry, for stars to shine, for life to exist. So what if the dark matter, the other 27%, is just as complex? This is the tantalizing idea of a dark sector. Perhaps there isn't just one dark matter particle, but a whole family of them. Perhaps they interact with each other through forces we have yet to discover, a dark electromagnetism carried by dark photons. If this were true, dark matter could have its own rich and complex behavior. It could form dark atoms, maybe even dark molecules. It could clump into dark matter stars that are powered not by nuclear fusion, but by dark matter annihilation. It could form dark matter galaxies with their own structures. Could there be an entire shadow reality, a parallel cosmos all around us, evolving according to its own set of physical laws, interacting with our world only through the gentle, persistent tug of gravity? This is, of course, pure speculation at the frontiers of theoretical physics. But it fires the imagination. It suggests the universe might not just be darker than we imagine, but infinitely more complex, with hidden layers of reality that we are only just beginning to conceptualize. The other side of the darkness: dark matter versus dark energy. Before we conclude, it's crucial to clarify one more thing. We've been talking about dark matter, the cosmic glue. But you'll remember from our cosmic inventory that the biggest player in the universe is something else entirely: dark energy. It's easy to confuse the two. After all, they're both dark, but they are thought to be completely separate and opposite phenomena. Dark matter is a form of matter. It has mass, it clumps together under gravity, and it's attractive. It's responsible for pulling material together to form galaxies and clusters. Its gravity is trying to slow down the expansion of the universe. Dark energy, on the other hand, is not matter at all. It seems to be a property of spacetime itself, a kind of intrinsic energy of the vacuum. And its effect is the opposite of gravity. It's repulsive. It doesn't clump. It spreads smoothly throughout the entire universe. And it's causing the expansion of the universe not to slow down, but to accelerate. This discovery, made in the late 1990s, was so shocking it won the Nobel Prize. It means that distant galaxies are flying away from us faster and faster over time. Dark matter is the architect that builds the cosmic structures, while dark energy is the force that is slowly but surely pushing all those structures apart. Together, they represent the two greatest mysteries in all of science: the 95% of reality that dictates the structure and fate of our universe, while remaining completely beyond our direct perception. Our perceptible world, the grand quest. So here we are, at the end of a 4-hour journey through the unseen. We started with a strange feeling, the intuition that there is more to the world than meets the eye, and we found that feeling echoed in the cosmos on the grandest scale imaginable. We've seen how the impossibly fast spin of galaxies, the bending of starlight around invisible giants, and the very architecture of the universe all scream for the existence of an invisible reality: dark matter. We've journeyed deep into the earth and smashed particles at unimaginable speeds in a relentless quest to touch this ghost. And yet, we've also confronted the uncomfortable possibility that this ghost may not be a particle at all, but a flaw in our most fundamental understanding of gravity itself. The fact that a theory like Mond can explain some observations so well, even with its own flaws, tells us that we must remain humble and keep an open mind. The search for dark matter is the single greatest detective story in human history. The clues are scattered across billions of light years, the suspects are exotic and elusive, and the stakes are nothing less than our entire conception of reality. What does it mean for us, living our lives on this tiny planet, that we are swimming in an ocean of invisible matter that shaped our very existence? It means that the universe is not just stranger than we imagine, it is stranger than we can imagine. It's a profound and beautiful reminder that we are just at the beginning of our journey of discovery. The quest continues, and the answer, whatever it may be, will undoubtedly change everything. Two possibilities exist. Either we are alone in the universe or we are not. Both are equally terrifying. Arthur C. Clarke.